Okay, should be recording. Hello everyone. Welcome to, I think this is week 7 of Introductory. Today we're going to be going over bases and decimals. My name is Will. Hopefully you know me by now. And TAing today is Andrew. He'll be answering all your questions, so please send him all your questions and responses, as I will not be able to look at chat for the duration of the class. A quick rundown of what we're going to be going over today. We're going to start talking about bases, so like base 2, base 4, hexadecimal. We're going to be talking about how to convert between different bases. We'll be talking about higher bases and how we use letters to represent values greater than 10. We'll also be going over base arithmetic, so doing addition, subtraction, multiplication in different bases. Then we're going to shift towards decimals. We're going to talk about terminating decimals as well as repeating ones. And finally, we're going to sort of combine the two topics together, bases and decimals, and we're going to be talking about representations of bases within decimals. And yeah, let's go ahead and get started. So starting off, basically when we do math, what we use is base 10, right? So let's say we have something like 16 plus 24. We know that the 6 plus 4 is equal to 10, so that carries over. And then we have the 1 plus 2 plus 4, and that's 40. And the reason we do things like that is because we group numbers in groups of 10. So like the 6 plus 4 here, this is 10. So we keep the 0 and then we carry over the 1. And when we're in different bases, it's essentially the same thing, except instead of grouping by 10, we group by like 9 or 8 or whatever the base is. And another important thing to keep in mind is how these numbers are represented. So in base 10, if we have a number like 615, well, this 5 is the units place. Each of these is worth 10 to the 0, which is equal to 1. And now we have the tens place, where each of these is worth 10 to the 1, which is equal to 10. And finally, we have the hundreds place, where each of these values is worth 10 squared, equal to 100. That's why this total number is equal to 6 times 100 plus 1 times 10 plus 5 times 1, which is equal to 615. And that's how it works in base 10. And as long as you keep this representation of numbers in mind, it's easy to switch between different bases. So yeah, let's talk about converting bases. So let me move the screen down a bit. Like I said earlier, keeping our base 10 representation in mind, if we have a number, let's just say A, B, C in base X, let's say, then this C here will be worth C times X to the 0. This B here will be worth B times X to the 1. And finally, this A here will be worth A times X squared. And this will continue on no matter how many decimal places to the left we go. We'll be going X cubed, X to the 4, X fifth, as many places as we need, basically. And that's essentially how you convert a number from base X to base 10. We just add all of these numbers up. We add this AX squared to the B times X to the first plus C times X to the 0. As long as we add all these numbers, then we'll get a base 10 number, some number in base 10, which is equivalent to ABC in base X. So I guess let's try an example. Let's say we have 435 in base 6, and we want to convert this to base 10. Well, like I said earlier, the rightmost decimal place corresponds to 6 to the 0. Since
Hey, Will.
Yeah.
Will, 1 second. Sorry to interrupt you, but could you make Naveen a co-host? He's also TAing today.
Oh, Naveen is here. Great. Yeah, let me go do that. Avid Mudcat. There we go. Okay, so now you guys can ask Naveen questions as well. Yeah, so back to what I was saying. We have 435 in base 6. So basically, this is equal to 6 to the 0 times 5 plus 3, or rather, let me stay consistent here. 6 to the 1 times 3 plus 6 squared times 4. And this number is equal to 5 plus 18 plus 36 times 4, 144. This is equal to 167, I think. So yeah, that's how we convert a number from base 6 to base 10. As long as we stay consistent with this format of using base x to the 0, x to the 1, as the more we move to the left, basically. And now, how do we convert back from base 10 to base x? Well, we're going to do something similar, but basically what we want to do is we start with the largest power of x that we can find. So let's say we have a number, what's a good number? 212. And we want to convert this from base 10 into something which is base 8. Well, we're going to want to start with the largest power of 8 that can fit inside 212. 8 cubed is 512, so that's too big. So the largest power of 8, which will go inside 212, is 8 squared is equal to 64. And how many times does this go into 212? Well, this goes into at most 3 times, because 64 times 3 is equal to 192. So that will make 3 our first, or rather our leftmost digit, because 212 is equal to 3 times 8 squared plus ... which we'll get to later. So now that we took away 192, let's subtract that. 212 minus 192 is equal to 20. So now we want, what's the next biggest power of 8 which fits inside? Well, that's just going to be 8 to the first, and it goes inside 20 exactly 2 times. So if we do 20 minus 2 times 8, that leaves us with 4. So this 2 here, that's our next digit within the representation. So far we have 3 times 8 squared plus 2 times 8 to the first. Now we're just left with this 4. And then we just write that as itself, because 4 is equal to 4 times 8 to the 0, obviously. And no more powers of 8 can fit into it other than 8 to the 0. So 324 base 8 is our final answer. And that's basically how we convert from base 10 to a different base. We just check for the largest power that can divide, or that fits inside the base 10 number, and then we just keep subtracting until we get to something that is less than the base x, and then we just write that as our last number. So let's try another example. So this is binary. As if you don't know, binary is basically a base 2, which everything is represented in either ones or zeros. And we're going to want to convert this from base 2 to base 8. And there's 2 ways of going about this. First, we can convert this number from base 2 to base 10 and then convert that base 10 number back into base 8. Or we have another faster way that I'll show you later. But let's try doing it the slow way first, just to get familiar with the concept of converting bases. So here we have 1 0 0 1 1 0 1 0 1 base 2. So in terms of powers of 2, this is going to be 2 to the 0, this is 2 to the 1, this is 2 squared, and so forth. So if we just add all of these up, so we have 1 times 2 to the 0, that's that, plus 0, plus 1 times 2 squared, and then we ignore the 0. This is going to be plus 1 times 2 to the 4. This is going to be 1 times 2 to the 5. We have 2 more zeros. And then we have our last one, which is 1 times 2 to the 8. And now if we sum all this up, this is equal to 309. So this number 10011001 in base 2 is equal to 309 in base 10. Now let's convert this back into base 8. Let me move the screen down a bit. So if we want to convert into base 8, we just do what we did before. The largest power of 8, which goes into 309, is 8 squared, and it goes into exactly 4 times. So that's going to be our leftmost digit, and 309 minus 64 times 4. That leaves us with 53. Now the largest power of 8, which goes into 53, is 8, and it goes into at most 6 times. So that's our second number. And then when we subtract that out, we have 53 minus 8 times 6. That's equal to 5. And since 5 is less than 8, that's our final digit. So our final answer is 465 base 8. So that wasn't too bad, but the way that we make this faster is, let's take a look back at this number. So if you realize that 8 is basically just 2 cubed. So every 3 numbers in the representation, in the base 2 representation, correspond to 1 number in the base 8 representation. So that means if we take numbers in groups of 3 starting from the right, we have 101, or let me use a different color. We have 101, 110, and 100. Instead of converting this whole thing, we can just convert each of these chunks of numbers into base 8. So 101, that's equal to 5 in base 8. 110, that's equal to 6 in base 8. And 100, that's equal to 4 in base 8. And these 3 numbers, they give us 465 base 8, just like what we got down below. And this works the other way around too. If we have a base 8 number like this, we can just write this out in terms of base 2, 101, this is 110, this is 100, to get our base 2 representation back. And this doesn't just work with 8 and 2, it works with any 2 numbers which are powers of each other. So if you had 2 and 4, every 2 digits in base 2 would correspond to 1 digit in base 4. And that's one way to basically make converting bases faster. Now, moving on, let's try a slightly harder problem. Let's take a look at this one. This is from the 2013 AMC 10A, and it asks, in base 10, the number 2013 ends in the digit 3. In base 9, on the other hand, the same number written as 2676 in base 9, and it ends in the digit 6. How many positive integers b does the base b representation of 2013 end in the digit 3? Basically, what this question is asking us is that it wants us to find numbers b such that when 2013 is divided by b, the remainder is 3. Because once we divide all the powers of b, that's going to be the number that's left over on the rightmost digit. So in terms of modular arithmetic, which we went over last class, this is going to be written as 2013 has to be congruent to 3 in mod b. Or basically, if we subtract 3 from both sides, this means that 2010 must be congruent to 0 mod b. Basically meaning that b must divide 2010. And since we're asked how many positive integers b make this possible, we just want the number of factors of 2010. So if we go back 2 lessons, I think, to the primes and factors, we know that the number of factors a number has depends on its prime factorization. So let's prime factorize 2010. 2010 is equal to 2 times 3 times 5 times 67. And since each of these exponents are 1, according to the formula, that means 2010 has exactly 1 plus 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 equal to 16 distinct factors. And that would be our answer. However, we have to keep in mind that in base B, the digits represented in base B can never exceed B minus 1. Basically, that means that if we have 2013, we can't have this represented in base 3, because if we have 3 times 3 to the 0, this is just equal to 1 times 3 to the 1. So instead, it should rather be represented as 2020. And basically, that's why every number in the base B representation, or every digit, must be less than B. So that means since our number is 2013 and we have it in base B, that means B must be greater than or equal to 4. So out of these factors of 2010, there's exactly 3 of them which are not greater than 4. 1, 2, and 3. Everything else is greater than or equal to 4, so it should be okay. That means in total we have 16 minus the 3 exceptions, and that's equal to 13 possible values for B. So moving on, let's talk about higher bases. So let's say we have a base that is greater than 10, and we want to express double-digit quantities, as in if we convert something to base 12, if we convert 12 in base 10 to base 13, well, 12 is less than 13, so we can't express it easily as the rightmost digit of the number, because let's say we have 12 in base 10, we want to convert it to base 13. We can't just write, let's say, like 101 and then just 12 really small in the last digit place. Instead, mathematicians came up with a better way to represent double-digit values when the base is greater than 10. And the way they do that is using letters. So in this table, this goes up to 15, or F, but this actually continues on forever. But basically, mathematicians started using letters to represent these values. So if we had 12 in base 13, then that would just be C13, because the C is actually 12, if that makes sense. So let's say we're trying to convert something from, let's say we have a b base 15. If we want to convert this back to base 10, well, this would just be b times 15 to the 0 plus a times 15 to the first. And if we look back at this table, b is equal to 11, so that's 11 times 15 to the 0. And a is equal to 10, so that's 10 times 15 to the first. So this is just 11 plus 150, which is 161. So basically, the only important thing to keep in mind about these letters is that their value starts at 10, and every one it increases, basically. So as long as you remember that a is equal to 10, you can essentially figure out what any letter means. And like I said earlier, this table only goes up to 15, which is all the letters used in hexadecimal or base 16. If we were to go further, such as like base 20, then we would have more letters to represent these numbers. So moving on, let's try a problem involving a base 11. This one doesn't quite use the letters yet, but let me read it out. A base 10 3-digit number n is selected at random. Which of the following is closest to the probability that the base 9 representation and the base 11 representation of n are both 3-digit numerals? So let's see what this question means. if we take a look at all of the base 9, if we take a look at all of the numbers in base 9 and base 11, which are written as 3-digit, which can be written as 3 digits, and then we convert those back to base 10, then we can see which numbers in base 10 satisfy the condition. So basically something like 800 in base 10. This will not be able to be written in 3 digits in base 9, which would make it not satisfy the condition. And the reason is because it would be able to 1 something 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 in base 9, because it's greater than 9 to the 3 or 729. So therefore this would have 4 digits. And if we want it to have exactly 3 digits, then that means we want to find the greatest 3-digit base 9 number and also the smallest 3-digit base 11 number. And then we'll just convert those to base 10, and every number in between should work theoretically. So what exactly is the largest 3-digit base 9 number? Well, since I mentioned earlier that in base B, the greatest digit that you can write is B minus 1, that means the largest digit in base 9 is 8. So the greatest 3-digit number in base 9 would be 888 in base 9. If we convert this to base 10, this is just equal to 8 plus 8 times 9 plus 8 times 9 squared, which is equal to 728. Now, in base 11, the smallest number written with 3 digits is simply just 100. And in base 11, this is equal to 1 times 11 squared, which is equal to 121. So every number in between these should satisfy the condition. And the total number of numbers here is 728 minus 121 plus 1. This is 608 numbers. And in total, there's a total of 900 3-digit base 10 numbers. So that's going to be the denominator of our fraction, since this problem is asking for a probability. If we have that, then this is equal to 152 over 252, which is our final answer. And in case you're wondering why we don't check the smallest 3-digit number in base 9 or the largest 3-digit number in base 11, the reason is that if we check the smallest 3-digit number in base 9, for example, that number is guaranteed to be smaller than the smallest 3-digit number in base 11. Therefore, it wouldn't be able to be written as a 3-digit number in base 11. So we can disregard that. Similar logic follows for checking the largest 3-digit number in base 11. That's going to be for sure not able to be written as 3 digits in base 9. So we don't need to check any of those. And that's why we only need to check the largest in base 9 and the smallest in base 11, which gives us this range specifically. Let's try a different problem. So this was actually on the online Amy that happened most recently. It was question 5. I think a lot of people actually missed this because it's very tricky. Like the wording can mess you up really easily. So you have to be really careful. I'll go ahead and read it. For each positive integer n, let f of n be the sum of the digits in the base 4 representation of n. And then we let g of n be the sum of the digits in the base 8 representation of f of n. And then it gives an example. F of 2020 is equal to 133210 in base 4. And the sum of those digits, 1 plus 3 plus 3 plus 2 plus 1 is equal to 10. And then we convert that to base 8, which is 12. And then the sum of those digits is 3, which is g of 2020. And then it says that let n be the least value of, let big n be the least value of small n such that the base 16 representation of g of n cannot be expressed using only the digits 0 through 9. And find the remainder when n is divided by 1,000. So for this problem, let's start at the n and then work our way back towards the beginning. So we want n to be the least value such that the base 16 representation of g of n cannot be expressed using the digits 0 through 9. If we can't express it from using only the digits 0 through 9, that means we have to express it using the letters we were talking about earlier. The smallest value, which can't be expressed using 0 through 9, that's just equal to a base 16. It's exactly greater than 9. It's just 1 greater than it, which is, remember, it's quote unquote 10, but we write it as a. So this is equal to g of n. Then that means, let's convert this back to base 10. This is equal to 10 in base 10. So now it tells us that g of n is the sum of the digits of the base 8 representation of f of n. So that means if we have f of n and it's some number, let's say like a, b, c, and this is in base 8, that means a plus b plus c is equal to 10. And this 10 is from right there. So we want to minimize this number too. And going back to earlier, the largest digit possible in base 8 is 7. 8 minus 1 is equal to 7. So that means the smallest possible number in base 8, which has a sum of its digits being 10, that would just be 3, 7. Since we want to put the largest digit in the units place, which has the least value, and then we put the remaining 10 minus 7 is 3. We put the remaining 3 in the 10, quote unquote, tens place. So f of n is equal to 37 in base 8. Now let's once again convert this to base 10. Converting this to base 10, this is just 7 plus 3 times 8, which is equal to 31. Now, the problem states that 31 is equal to is the sum of the digits of the base 4 representation of n. So let's say we have a number a, b, c, d, e in base 4, and that means a plus b plus c plus d plus e is equal to 31. And again, we want to minimize this number. So how do we do that? We do the same thing as we did with f of n in 37. We know that in base 4, the largest possible digit is 3. So we want to fit as many 3s as possible near the end, or rather the right-hand side of the number in order to minimize it. So 31 is equal to 1 plus 3 times 10. That means in base 4, our smallest possible number is 1, 3, 3, 3, 3, 3, 3, 3, 3, 3. Is that right? No, one more 3. This is a total of 10 3s. And this is a 1. So if we add all this up, 1 plus 10 times 3, that's equal to 31. And again, this is in base 4. So if this is the smallest number which satisfies the conditions given in the problem, then all we have left to do is just convert this to base 10. Converting it to base 10, we have that n is equal to 1 times 4 to the 10 plus 3 times 4 to the 9 plus 4 to the 8 plus 4 to the 7 plus 4 to the 6 plus 4 to the 5 plus 4 to the 4 plus 4 to the 3 plus 4 to the 2 plus 4 to the 1 plus 4 to the 0. And I will spare us the calculations, but this is just equal to 2097151. And since the question asks us the remainder when n is divided by 1000, that just means the last 3 digits, so our answer is 151. So that wasn't too bad. We just had to be very careful and make sure we read the problem right. Moving on, let's talk about base arithmetic. So let me just move the page down, I guess. When we're adding two numbers in base B, for example, like I said at the beginning of the lesson, we just have to ensure that we carry over once we reach B. So if we had like 14 base 7 plus 25 base 7, well, let's write it like this, I guess. We have the 4 plus 5. 4 plus 5, that's equal to 9 in base 10. But in base 7, that's equal to 1, 2. Because we have 7 plus 2. 1 times 7 plus 2 is equal to 9. So we just write the 2 here, and then we carry over the 1. And then we have 1 plus 1 plus 2. And that's equal to 4. 4 is less than 7, so we don't have to carry it over. So we just write it as it is. So that's 42 in base 7. And then a similar process applies to multiplication and subtraction, as long as we remember numbers come in groups of B. And actually, you're not going to see too much of straight up base arithmetic in problems. What's more common is you're going to see that you'll have to convert it back to base 10 somehow using variables and then compute the calculations that way. So I'll show you an example of one of those problems. We have this equation, 34 in base B times 6 in base B is equal to 226 in base B. And the problem asks us, in which base is this true? So far, we can safely assume that B is greater than 6 because, once again, we can't have digits in bases which we can't have. If we have base B, we can't have digits less than or greater than or equal to B. That's what I'm trying to say. So that means B has to be greater than 6. So from here, we're going to write 34 base B, 6 base B, and 226 base B. We'll write those all as base 10 expressions involving B, and then we'll substitute them back into the equation. So 34B, it's not writing, hold up. 34 base B, this is equal to 3 times B plus 4. 6 base B, that's just equal to 6. And finally, 226 base B, this is equal to 6 plus 2 times B plus 2 times B squared. So if we plug these back into the equation, we get that 3B plus 4 times 6 is equal to 2B squared plus 2B plus 6. So now we'll just distribute the left-hand side. 18B plus 24 is equal to 2B squared plus 2B plus 6. And then we move everything onto the same side. Get that 2B squared minus 16B minus 18 is equal to 0. We'll divide both sides by 2. B squared minus 8B minus 9 is equal to 0. And now we factor this quadratic. This is equal to B minus 9 times B plus 1. And this gives us two solutions for B. B is equal to 9 or negative 1. But obviously bases cannot be negative, at least not that I know of. So that means our answer has to be B is equal to 9. So yeah, now let's move on and talk about decimals. In base 10, decimals are just numbers after the decimal place. So if we have 0.65, this means that 6 is in the 10th place, which means that it is worth exactly 1 over 10. And then the 5 is in the 100th place, which is worth 1 over 100. and this is equal to 10 to the negative 1, and this is equal to 10 to the negative 2. So that means our total decimal is equivalent to 6 times 1 over 10 plus 5 times 1 over 100, which is 65 over 100, which is what I'm sure y'all are very familiar with. And basically this continues on. For every, I guess, the ith place right of the decimal point is worth exactly 10 to the negative I. So the first place to the right is worth 10 to the negative 1. The third place to the right is worth 10 to the negative 3. And so on. Now let's talk about two different types of decimals. Or rather, yeah, two different types. So we have terminating decimals. Terminating decimals are those which end after a certain point and do not go on forever. So an example of a terminating decimal would be 0.4 or 0.819283. These are terminating. They don't go on forever. Something which is not terminating is like 1/3, which is 0.33333, ... which we represent as 0.3 bar. And the bar just represents the part that repeats. Another repeating or non-terminating decimal would be 0.06 bar. That means the 06 would repeat forever, so it's 0.06060606. And keep in mind, this is different from, it's not equal to 0.06 with the bar just over the 6. Since the bar is not over the 0 would only happen once, but the 6 would repeat forever. So that's equal to 0.06666666. So these are not equal. So it's important to look at where the bar is, because I've definitely messed that up before. So yeah, terminating decimals. So what makes them different from non-terminating decimals is that in reality, you can tell they're terminating because in their fractional representation, which every rational decimal has, the denominator only has powers of 2 or 5. So let's say we have 1 over 2 squared times 5. This is equal to 1 over 20, which is equal to 0.05. This terminates. Similarly, 1 over 2 to the 4 times 5 squared, 1 over 400, 0.025. This also terminates. But as soon as we introduce powers that are not 2 or 5, it's like 1 over 3 times 7, 1 over 21, this is equal to 0.416 repeating. This does not terminate. So a fraction or a decimal only terminates if the denominator of its fractional representation only has powers of 2 or 5. And this leads into our next question, which is pretty straightforward if you keep that in mind. This question asks, what is the smallest positive integer n such that this fraction n over 4680 excuse me, n over 4680 can be expressed as a terminating decimal. So that means we want this fraction, n over 4680. This must only have 2's and 5's in its denominators. So if we factor out 4680, we get that, or not factor out, if we factor 4680, we get that this is equal to n over 2 cubed, that's hideous, 2 cubed times 3 squared times 5 times 13. And if we want the denominator to only be left with 2's or 5's, that means we need this 3 squared and this 13 term to cancel out. So that means n must contain at least 3 squared and 13. So that means n is equal to 3 squared times 13. And then again, if we divide this by 2 cubed times 3 squared times 5 times 13, these would cancel out. This would be 1 over 40. which does indeed terminate. So that means our smallest possible value of n is 3 squared times 13, which is equal to 117. Now, the opposite of a terminating decimal, that is going to be a repeating decimal. And repeating decimals are basically ones which continue forever in a fixed pattern. So like not pi, because pi is irrational. It doesn't follow a pattern, 3.14 ... Or like square root of 2, 1.41, I think. These are irrational because they don't happen. They don't follow something wrong with chat. Hold on. Okay, it looks like it's good now. Sorry about that. I don't know what happened. But yeah, as I was saying, these two are irrational. They don't follow a fixed pattern. Whereas repeating decimals, they do. So like 2 over 7, this will 2.2857114, and this repeats infinitely. And the most important repeating fractions to keep in mind. Why is chat open again? It's weird. Okay, that's interesting. But yeah, the most important repeating fractions to keep in mind are 1 over 9, 1 over 99, 1 over 999, and so on. And because these each represent 0.1 repeating, 0.01 repeating, 0.001 repeating. And you can essentially make or more or less any repeating decimal of these. So let's say we have 0.683 repeating. That just means 0.683 times 0.001 repeating. So it's 683 over 999. So that's why these three fractions are important. 1 over 999, 1 over 99, 1 over 9. And not just these three, sorry, like every one which is made up entirely of nines. So let's try a problem. So the problem states that for a certain positive integer n less than 1000, for a certain positive integer n less than 1000, the decimal equivalent of 1 over n is some repeating decimal with period 6. And then the decimal equivalent of 1 over n plus 6 is some repeating decimal with period 4. And the question asks, in which interval does n lie? So if 1 over n can be represented as a repeating decimal of period 6, then that means n must be a divisor of 999,999. And also, n cannot divide n 99999, 9999, 99999, or 9. And the reason for that is because if it did, then the decimal would not repeat every 6 digits, but rather one of every 5, 4, 3, 2, or 1. So therefore, n must satisfy these two conditions. Similarly, if 1 over n plus 6 can be represented as a repeating decimal of period 4, then n plus 6 must divide 9999. But it cannot divide 99999 or 9, because once again that would mean it will repeat with a period less than 4. So let's start by looking at the factors of 9999, because that's a lot simpler to look at than the factors of 999999. So looking at the factors of 9999, we have 1, 3, 9, 11, 33, 99, 101, 303, and 909. And straight off, we can eliminate a few of these. We can eliminate 1, 3, 9, 11, 33, 99. Because these divide one of these three numbers, which means that it will not repeat with a period of 4. So we have these three remaining numbers, which is equal to n plus 6. So if we subtract 6 from each of them, that gives us the possible values of n are 95, 297, and 903. And this value of n must also divide 999999. And the only one which does so is this middle one. So our final answer is 297. So yeah, now let's take a look at decimals and bases combined together. So when dealing with these, basically, let me move the page down a bit. If we have a decimal, the ith place to the right of the decimal point is now not worth 10 to the negative I, but rather b to the negative I. So let's say we have 0.12 in base b. This is worth 1 times b to the negative 1 plus 2 times b to the negative 2. So it's 1 over b plus 2 over b squared. And basically, this is like the exact same thing as with integers in base b. It's just we're going in the opposite direction with negative exponents instead. So let's take a look at a problem. The problem states that a rational number written in base b is ab.cd, where all digits are non-zero. The same number in base 12 is written as bb.ba. And it asks for the base 10 number abc. So basically it wants us to find a, b, and c. So if we have these two numbers and they're equal, that means their integer parts and their decimal parts must be equal as well. So we have AB in base 8 is equal to BB in base 12, and point CD in base 8 is equal to point BA in base 12. So let's write these out as expressions involving A, B, C, and D. So from this first equation, we get that 8A plus B is equal to 12B plus B. And from the second equation, we get that C over 8 plus D over 64. That is equal to B over 12 plus A over 144. So let's take a look at this first equation. If we cancel out the b on both sides, we're left with 8a is equal to 12b. Oops. 8a is equal to 12b. So a is equal to 3/2 times b. And we can plug this back into the second equation to get that c over 8 plus d over 64 is equal to b over 12 plus a over 96. or sorry, not a over 96, b over 96. And this is just equal to 3b over 32 once we combine common denominators. So let's get rid of the fractions on both sides by multiplying everything by 64. So let me move the page down a bit. We are left with 8c plus 8c plus d is equal to 6b. So from here, we have to guess and check. And we know that all the values a, b, c, and d are less than 8 since ab.cd is written in base 8. So that means that for our pairs of a and b, remember that a is equal to 3/2 times b, we have 3, 2 and 6, 4. These are two possible values for the pairs of a and b. Let's just go ahead and try the first one. This gives us that b is equal to 2, so that means that 8c plus d is equal to 12. And one natural solution to this is c is equal to 1, d is equal to 4. And that basically just solves the problem. We don't even have to bother checking it, but the second case doesn't work. So that means we have a is equal to 3, b is equal to 2, and then c is equal to 1, d is equal to 4. So the 3-digit base 10 number ABC is just 3, 2, 1. And yeah. Now let's try one last problem before we end off today. This problem, 2004 AMC 12A. I think it was the number 25, I'm not sure. But for each integer n greater than or equal to 4, let an denote the base n number, and the an here isn't a base n, it's just like it's a subscript here. Let an denote the base n number 0.133 repeating in base n. And then the product of a4 all the way to a99 can be expressed as m over n factorial, and we want the smallest value of m. So for this problem, let's first come up with a way to write an. So we're told that an is equal to 0.133133 in base n. So if we write this out as a fraction, this is equal to 1 over n plus 3 over n squared plus 3 over n cubed plus 1 over n4 plus 3 over n5 plus 3 over n6 . And basically you'll realize that these three terms, they're just the first three terms each multiplied by 1 over n cubed. So what that's telling us is that this is an infinite geometric series, with the initial term being 1 over n plus 3 over n squared plus 3 over n cubed. And the common ratio, r, is equal to 1 over n cubed. That's an ugly looking 3. 1 over n cubed. So keeping this in mind, we can apply the formula we learned about the sum of a geometric series, I think 3 classes ago. And that would just be equal to, or rather I should write an is equal to the initial term 1 over n plus 3 over n squared plus 3 over n cubed divided by, or here we'll just write as a fraction, 1 minus the common ratio, 1 over 1 minus n cubed. So that's our expression for an. So let's simplify this a bit. Ultimately, we're going to be looking for something telescoping here, since we're asked for the product of these terms from 4 all the way to 99. And there's no way that we can possibly like go through all 96 values. So we're going to have to look for something to cancel out. But first, let's go ahead and simplify this. This is equal to, let's see, 3n, or let me write this, n squared plus 3n plus 3 over n cubed. So we're just combining common denominators here. And then we're multiplying this by n cubed over n cubed minus 1. So these two terms cancel out, and we're just left with n squared plus 3n plus 3 over n cubed minus 1. And since we're looking for these to cancel out, we're going to try and look for something with an n cubed term minus 1. And in order to do this, we're going to multiply both top and bottom of this equation by n. So times n times n. And this gives us n cubed times 3n squared plus 3n over n times n cubed minus 1. And the motivation for this is realizing that this term right here really looks like n plus 1 cubed. So we're going to make it n plus 1 cubed, but we're missing a 1, so we just subtract that into n. So we do n plus 1 cubed minus 1, because we don't have a 1, and over n times n cubed minus 1. So here we successfully set up our telescoping, because for every 2 consecutive terms, this will cancel out with this term of the previous, or rather not all of that, just this part of the previous term. So let me write it out to make it more clear. We had, let's do A4, A5, all the way to A99. This is equal to 5 cubed minus 1 times 6 cubed minus 1, 7 cubed minus 1, all the way to 99 cubed minus 1. And then on the bottom, let's separate the n term and the n cubed minus 1 term. So we have 4 times 5 times 6 times times 99. That's the n term. And then for the n cubed minus 1 term, we have 4 cubed minus 1, 5 cubed minus 1, all the way to 99 cubed minus 1. And also, sorry, this top part goes to 100 cubed minus 1, not 99 cubed, because it's n plus 1 cubed minus 1. So this goes up to that. So you'll see that these terms all cancel. And in the end, we're just left with 100 cubed minus 1, which is 999999, divided by 4 times 5 times all the way to 99 times 4 cubed minus 1, which is 63. So I'll go ahead and spare you guys the calculations, but this is essentially equal to 13 times 37 times 33 times 6 divided by 99 factorial. And then we can also cancel out the 99 to give us 962 over 98 factorial. And this is the expression which has n as small as possible. So therefore, the problem is asking us for the numerator of this, and that is just 962. So our final answer is 962. And so yeah, that is last thing I have for today. Does anyone have any questions about anything? Well, if no one has any questions, thank you all for coming. If you guys do have any questions after the class, feel free to post them in our Discord, AOPS forum, anything really. We'll try to get back to you. Yeah, bye guys. Handout should be out shortly after the class. Sorry about the issues with the chat. Don't know what was going on with that. Thank you guys. Bye. Someone asked why didn't Naveen leave? Probably because he was busy. And let me stop the recording actually.